Infrastructure is crumbling and the problems are only getting worse. The pressure to find solutions is hot. Let's talk about why American cities have no water, no electricity, and no money to fix their infrastructure problems. Welcome to the Infrastructure Hot Seat Podcast, hosted by Chad Smeltzer.
Hi, everyone. Welcome to the Infrastructure Network. My name is Chad Smeltzer. I am your host. Today's guest is Kevin Frank, who is a wastewater process engineer. Thanks for joining me, Kevin.
Well, thank you, Chad. Happy to be here.
Kevin, how long have you been in civil infrastructure?
Well, I started working in the wastewater treatment business about 2002 at the Scranton Wastewater Treatment Plant in northeastern Pennsylvania, and I've been doing consulting engineering on the process engineering side for about 24 years now. So it's been a fun journey so far.
That's 24 years, man. That's a long time. Did you go to college?
Yep. Yeah. I got my bachelor's of engineering degree in environmental engineering in 2003 from Wilkes University, also in northeastern Pennsylvania. Completed a master's degree while working full time in the Harrisburg area. I'm at Penn State, and been working at AECOM now for about 17 years. So I've been with two different firms, and before that, the Scranton Sewer Authority. So it's been a lot of fun.
It's kind of one of those questions where I ask, like, did you go to college? Like, where'd you go to college? Everyone that has a PE goes to college typically and gets their PE, right? Silly question. But all right, so wastewater. What made you want to get into wastewater? What attracted you to wastewater, first of all?
Well, it was I always had this interest in water quality and purifying water and making it as clean as you can get it for different purposes. And so I started out originally when I was in college, even back in high school. I had a little business installing and maintaining saltwater reef aquariums and garden ponds, and getting into designing the filtration equipment for just purifying the water to keep fish alive. And so I gradually learned more and more about biological filtration, a nitrogen cycle, how to remove ammonia, how to remove nitrate. And that led me to get really interested in how can we kind of scale these filtration equipment up to treat much larger flow rates of wastewater flow. And that's really what got me into wastewater treatment is designing facilities and infrastructure and civil engineering reactors to purify wastewater. And so it was kind of an interesting similarity between the type of filtration systems you need for aquariums and garden ponds and wastewater treatment. They're very similar, just a much larger scale. We do this for wastewater infrastructure.
That is interesting because my dad ran wastewater and water treatment facilities too in Pennsylvania, ironically, in Wrightsville, Pennsylvania. And that's how I got exposed to it. And when I was 15, I worked at the plant with him and public works and stuff. But he always had an aquarium when I was a kid. And he always loved messing with the chemistry within the water. And he's like, oh, there's an algae outbreak or something like that. I was like, how do you know? Like, what do you mean by that? So
yeah, you got to test the water. You have to make adjustments as necessary.
Yeah, because it's never perfect. It always changes. Dynamics change. You know, as the fish use for bathrooms and stuff, like, it changes dynamics of the water. You know, all that stuff that plays a big role in filtration. So what's the biggest aquarium you had?
Oh, I've had a couple 150-gallon saltwater reefs. I don't do a lot of saltwater reef work anymore. I do have a 200-gallon Lake Malawi cichlid tank that I still maintain, and I have a big 6,000-gallon koi pond out back as well with waterfalls, and it's got its own wastewater treatment plant in the garage. It's actually what we call an MBBR, which is a moving bed biofilm reactor, and so it's about almost a cubic yard of this plastic media that rolls around in the water with an aeration system, and those little pieces of plastic media grow specific types of bacteria on it to remove ammonia and convert it to nitrate. And so it's a much smaller scale type reactor than exactly what we put in a lot of wastewater plants. So we actually do MBBRs for wastewater treatment. They're usually smaller plants, often used on cruise ships and small, like rest stop size treatment plants. But it's really interesting to me to have a hobby that kind of blends what you do as a living, basically. So I got to design and build and operate my own wastewater plant in my garage for the koi pond using a lot of the things I learned as being a professional engineer in the wastewater treatment industry.
That's really cool because you basically had a hobby that turned into a profession, and then during your as a hobby, you're tweaking your skills to go into your profession because you're learning out in the field too, and then now you're processor, processing all this information for wastewater treatment plants all over the East Coast or world now, right? Is that what we talked about?
Yeah, yeah. I mean, I started in basically doing consulting engineering in the Harrisburg, Pennsylvania area. And eventually I moved down to Maryland. I guess it was around 2008 or 9 I came down to Maryland because there was so much engineering work needed in the Maryland area for what we call an E&R treatment standards. So that's enhanced nutrient removal. That means we have to get the wastewater effluent from a treatment plant down to 3 milligrams per liter total nitrogen and zero point 0.3 milligrams per liter total phosphorus. And meeting limits that significant that's a lot of process engineering and a lot of process modeling that we do to meet those treatment limits. And so everything I learned as a professional doing that sort of work, I kind of applied to these hobbies as well. So they all became integrated. It's kind of interesting.
That is interesting because you're in Pennsylvania and I grew up in Pennsylvania. And the Chesapeake Bay Initiative was huge for reducing the phosphorus and nitrogen back, I think, 20 years ago now, something like that.
Yeah. When I was still in Harrisburg, they had BNR limits, so biological nutrient removal. It's kind of like the first tier of removing nitrogen and phosphorus from wastewater, and we're usually looking at around 6 to 8 milligrams per liter as a target for nitrogen in the effluent in Pennsylvania for the Chesapeake Bay initiatives. And I think it's about 1, maybe 0.8 milligrams per liter of total phosphorus. And so that was fairly strict. And a whole lot of treatment plants in Pennsylvania had to do very significant costly upgrades to meet these new limits to protect the Chesapeake Bay. Now in Maryland, where we're closer, because the wastewater discharge is even closer to the bay, they rolled out limits of even more strict requirements. So they were already doing BNR before Pennsylvania did. And then Maryland and even some parts of Virginia had to meet these ENR level treatments, which really decreased the amount of nitrogen and phosphorus loading into the Chesapeake Bay.
So what is the significance of having too much phosphorus and nitrogen in the water?
Well, what you have when you've got a lot of excess algae and phosphorus, you get a lot of algae growth. And when you have a lot of algae growth in natural waterways, tends to clog up the waterways and it removes oxygen. Believe it or not, as this algae grows and then decays, it consumes a lot of oxygen and can result in a lot of algae, even more algae blooms, which then consumes more oxygen. And you get these dead zones of oxygen where fish can't live. And so it's all about trying to protect the habitat of the fish. So it kind of comes back to protecting the environment from these algae blooms.
Yeah, because that can have a huge impact on the fish, and just seeing a bunch of dead fish floating down a river is never fun to anybody.
No. That's why we have to continuously keep being resilient. And the other thing that ties into that is not only do we have to meet more strict effluent limits, getting nitrogen and phosphorus and other pollutants down lower and lower, we also have this blooming population of people. And so with the population continuously to grow and grow, we're making more and more wastewater. And so we've got more wastewater and we have to treat it to even higher, more strict limits. And so this is when process modeling and being able to figure out how to upgrade a treatment plant to get the nitrogen and phosphorus pretty much as low as you can get it. That's where a lot of the newer process modeling technologies have really become much more popular than, say, they were 10 or even 15 years ago. And so that's kind of where we keep going at this point is using more enhanced tools to meet lower limits.
Yeah, that's a great point. You're talking about technologies, which I want to get into a little bit more. But if the let's just stick to America, right? With the phosphorus and nitrogen limits and things like that. When just from being from Pennsylvania, I remember all this because there was a lot of fees and expenses that the ratepayers would have to absorb because of these implementations of the limits, right? How do you think that impacts, cities' budgets and stuff?
It's quite a burden. And to give you, a lot of examples, there's a lot of Rust Belt cities out there that have old infrastructure that's been around for sometimes 50 or even more 60, 70 years they've had these wastewater treatment infrastructure installed and running, and they're starting to fall apart. And there's not a lot of funding out there to provide a lot of upgrades to this plant. There are several means. There's federal and state grants you can get, but when a treatment plant is faced with a $50 million upgrade, that ultimately mostly has to be funded by the ratepayers, the people within the service area of the infrastructure. And a lot of state departments and even federal departments can provide financial aid for that if you go through funding sources. But it usually results in a higher sewer and water bill for people. And so what we have to do as professional engineers is figure out the best, most economically feasible way to upgrade treatment plants. So if you've got a typical, let's say a $50 million upgrade for a plant, we have to task ourselves with being able to figure out how to do that same level of treatment, but at less cost to the ratepayers. And so that's really where all this enhanced process modeling and process engineering comes from, and what it's for is to try to keep the cost down as much as we can.
Yeah, that makes a lot of sense, because if you hit the ratepayers with too much, expenses, and it hits their wallets, you get a lot of pushback, and these, city councils and things like that have to deal with a lot of that, especially when you're talking about a $50 million upgrade to the plants. What do you think about the PFAS and the forever chemical stuff that's going on now too?
Well, it's certainly a very new topic, and these forever chemicals. We've done a lot of research on endocrine disruptors and emerging contaminants of concern. PFAS is kind of in the same ballpark, where we're producing so much stuff out of plastic. There's plastic everywhere now. It's clogging the oceans. It's clogging waterways. It's waste that kind of goes around. And it just stays around so long. Stuff takes so long to biodegrade, and PFAS can be a part of that, of a lot of this excessive use of plastic. And it's really something that's going to continue to grow and be more and more of a problem as we go on. There are some new limits being proposed and discussed at higher levels to force drinking water plants, and even sometimes wastewater plants. There's been discussions of adding treatment steps to remove these PFAS chemicals. And so nowadays everything's getting harder and harder and more difficult, with bigger and greater challenges to keep the water as clean as we can.
Yeah. No, good points, because we're talking like a 0.004 parts per trillion now as a level of removal, which is pretty significant. I mean, that's going to cost a lot, I would imagine.
Yeah, when you get to these really high levels of treatment, you start to go to technology like reverse osmosis. Oh, sure, no problem. I was just going to say that these higher levels of treatment get more and more energy intensive, and so like if you went to a reverse osmosis plant, which is pretty much the highest level regular removal you can get, it can get extremely small particle removal, including these PFAS things. And what happens is you end up with very high treatment costs. So we're protecting the environment, and we're cleaning up the water, but we're using a whole bunch of electricity to do it. And that usually ends up as greenhouse gas emissions and causes more air pollution issues, leading to climate change. And so, we have to find this balance. How clean do we make the water without causing too much other pollution from electricity consumption? And it's getting to the point where are we at a point where we can't really afford to clean it anymore, or do we keep going?
Yeah. No, good points. Because if we don't get the PFAS out of the systems, that's the water itself. We're still putting ourselves at a huge risk of diseases and things like that could come out of those things. But when you're talking about all the plastic, I was thinking about this last night. Everything's as plastic. We got delivery from from a restaurant to eat dinner. And I'm throwing away all these. I didn't throw away the plastic. We use it, recycle as much as we can, but. I mean, just imagine one household, how much plastic they use these pods. I was thinking about these pods that you throw in the washer and dryer and things like that. That's plastic that melts and goes into the waterway. How are we letting that happen? Like, it doesn't make sense to me.
Yeah. It's a lot of corporate mentality, where if we can sell the same product in a fancier package, we can sell more of it, or we can sell less of it for the same price. So if you go buy dish detergent, you can get a 5-pound box for $10, but you can get the little pouches. You get half as much product, but it's the same price. It's almost like a marketing ploy to me. It seems to move less product and charge the same amount and increase your profit margins. And it's just it's unnecessary. It's all this extra plastic.
Yeah, and I don't want to get down the rabbit hole too far, but I do want to address it because it's the future of what we're trying to do in treatment, because phosphorus and nitrogen was, something we were focused on 20 years ago. Now we're focused on PFAS and forever chemicals that are in the system. It's like, where do we eventually have to hold someone accountable who the pollutants are and who are they and what are they doing to address the cost of these upgrades that are going to, the taxpayer can only pay so much based on how many, taxpayers there are in a demographic, right? So you can't just be charging all this money and not have anybody be held accountable. So it's very interesting how we're going to, overcome some of this stuff. Is there really a filtration in your just opinion? Sorry, in your opinion, is there some product or is there a technology out there to remove PFAS?
I mean, there's, like I said, you with reverse osmosis is probably about the highest level of treatment you can get. I personally don't have the research or knowledge on PFAS removal with reverse osmosis, but I know that there's other things like endocrine disruptors, things that can change, go right down to the DNA. A lot of animals that is in water nowadays. And if you have a treatment plant with multiple barriers, so you have primary treatment, you've got secondary treatment with activated sludge, and you can go to more refined treatment like filtration and chemical addition to precipitate out other things. If you make your reactor large enough, a lot of these endocrine disruptors will eventually biodegrade over time within the system. What that usually relates to is a larger tank and a larger, what we call a solids retention time in the process to help biodegrade these other compounds. But at this point, as far as PFAS removal, there is some technologies out there. It's not exactly my forte. It's not my area of expertise, but we are starting to really pioneer and find out how to remove this stuff because the limits, it's like they're going to come around eventually.
Yeah, there's no doubt. There's going to eventually be the limits are going to have to be put in place, and there's going to have to be removal, and then someone's got to pay for it. That's the key. What that looks like, nobody really knows, but there is some things that were put out there. 3M paid $12 billion over 12 years or something like that to help cover the cost. And like I said, I don't want to go to the political side of this, but that's what it's going to take. We have to put the contributors on notice that someone's got to pay for this because they're talking about billions of dollars per state that are going to have to implement this treatment.
Yeah. And it's, when Teflon came out and it was the magic nonstick coating that everybody started putting on pans and things. It was a miracle time saver, help you clean your plates and your dishes. But a lot of that stuff really caused a lot of environmental problems. And source control is the best way to do it, to prevent it from getting in the water in the first place. Just stop making these products.
Right. I'm with you 100%, man. So, well, I want to segue into technology now because, we know there's the problems, the phosphorus, nitrogen, the PFAS, the forever chemicals that are in the waters. Now we have to figure out what technologies and processes are out there. And I'd love for you to kind of comment on like what you're seeing the future of process, wastewater treatment processes and what that looks like.
Sure. Well, anytime we get if a client comes to us and says we need to expand a treatment plant and we have to meet more stringent limits, usually we're talking about nitrogen and phosphorus, BOD, suspended solids, and having to meet some sort of disinfection standard as well. And so what we've kind of gravitated towards in the last, say, 15, even 20 years is this notion of process modeling and doing simulations in a computer. So what we often do now for most projects is we develop a process model of the treatment plant, and we build this model in a computer. There's various software packages out there to do this. There's EnviroSim makes BioWin, Hydromanis makes GPSX, and Dynamita makes Sumo. And these are all really great software packages that we use to build a treatment plant within a computer. And we calibrate it to existing data, or sometimes we'll do an intensive sampling program where we sample for nitrogen, phosphorus, solids, all sort of different parameters at various different locations in the plant. And once we have all that data, we kind of build a little mass balance and show how solids, nitrogen, and phosphorus are moving around within the treatment plant process. And once we've got a kind of a benchmark with the sampling data, we try to calibrate a model to that. And so we can dynamically calibrate a model and show how the model predictions either line up or don't line up with the actual measurements. And so once we've got a model kind of tuned and dialed in to actively and accurately predict process performance, then we can run simulations for future conditions, whether it be a higher a surface area expansion that has higher flow rates or higher solids loadings, higher nitrogen loadings, and figure out how to reorganize the treatment configuration, whether it be adding anaerobic zones, which are unaerated, or anoxic zones, and aerobic zones, and trying to partition out reactors with the right proportion of those zones to get you the best level of treatment performance you can. And so that's what we're really been using process modeling for a number of years, and that'll continue. I think these process models, they can be updated and refined to account for other things like PFAS, for instance. And I think maybe we'll get there someday. We're not quite there yet, but that's certainly something that could be in the cards.
Yeah, those sounds like there's a lot of options now for removal of these chemicals and the phosphorus and nitrogen, which are super important. And being able to model them efficiently with the technology sounds like it's going to be a little more cost effective. And then what is your opinion of AI in the future with all this?
Well, there's been a lot of push to integrate process modeling with artificial intelligence. There's some process models that have been around actually for quite some time. There's a few firms out there that will create a process model for you that actually learns from the data it gathers over time, and it can start to kind of self-calibrate it. That gets really, really advanced, and it gets rather complicated. But it can be done, and it can be managed if you've got dedicated folks around that can continuously update and continuously tune and monitor the performance of your online process model. And they can actually be used to change operational parameters like recycle rates and dissolved oxygen set points and things like that. The model can actually start to make those operational changes on its own. So a plant starts to quote unquote run itself more. But it does take a lot of oversight and a lot of, there has to be people that know the process modeling and that can continue to tune it and observe it and make sure it's working well. But really, it all comes down to how comfortable is the operator of the treatment plant with this new technology. Yeah. Are they okay with allowing the model to make adjustments to the plant? This is where you start to walk this fine line of who's running the plant, the model or the operators, and it always should be in the operator's hands.
That's a great point, because nowadays the AI is becoming pretty advanced, it seems like, and the more we train these models, the more the concern is that it's going to take jobs and things like that. I don't ever think there's something that's going to replace somebody. A human's going to make better decisions on certain emotional things. There are certain things, maybe not emotional, but that are going to be needed that an AI system cannot overcome, because it doesn't have all the pieces to the puzzle, so to speak. I guess that's what I'm getting at. What do you think about the time it takes to build build a design for a treatment facility, I guess, from scratch versus something that's already in place? What does that kind of look like? Something from scratch with process modeling, building a facility versus something that's already established, that's built, and you can implement process modeling there.
This is an excellent topic. When you've got what we call greenfield plants, where there is no plant in existence yet, that's kind of an engineer's dream. Our firm is actually designing a huge brand new treatment plant for Salt Lake City right now, and that was one of the most recent greenfield style plants. There was a plant already there, but we're basically building a whole new plant that does much higher levels of treatment than the existing plants. We're building a whole new plant next to the old one, so that when the new one comes online, we can shut the old one down. And so these greenfield plants are just the greatest project you can get, is where you have control over the sizing of tankage and things like that. But it's more challenging, and sometimes I consider it a little bit more enjoyable, is when you have an existing plant and you have to make it do new things. So you got a plant that was designed only to remove ammonia, and now you have to, one, make it handle more loading to serve more people, and get it to treat to higher levels. And so it's kind of it's a double whammy kind of thing. It's where you've got to do two different big objectives. And that's where process modeling gets really helpful and useful. So if you have a large aeration tank that's fully aerobic, now we can use the process model, if well calibrated, to carve out anaerobic or anoxic zones, and figure out how we can make an existing plant do more for less money, as opposed to building new tankage. We always say the cheapest tankage at a treatment plant is the tanks that are already in the ground. And so we have this notion of infra-stretching, where we're trying to get existing infrastructure do more without having to build more. And it's all about cost savings, trying to limit the, ratepayer hikes and do more with less. That gets more difficult, more challenging, but that's where the process modeling really does help us out quite a bit.
Yeah. Thank you so much for explaining that, because I was wondering myself, and I'm sure the audience was thinking the same thing, like, what's the difference, and how does that impact how process modeling is designed and implemented? So very good response there. So we're at the end of the show, Kevin. What's the best way, if anyone has any questions, to kind of reach out to you and get connected?
Well, sure. They can contact me by email. I'm at kevin.frank@aecom.com. That's probably your best way to get in touch with me. I'm happy to take any emails with questions.
I appreciate that, man. Thank you so much for joining the show. We thank you for giving us your insights on everything wastewater process modeling, because it's one of those things no one really talks about that much. So we appreciate you coming on the show and talking about it.
Well, sure. It was a real pleasure to be here. Thanks very much, Chad.
Thank you for listening to the Infrastructure Hot Seat Podcast. We hope that this show brought you some insight on relevant topics within the infrastructure world. Please join us every 2 weeks on Tuesday for the next episode. If you're interested in being a guest on this podcast, please set up a 15-minute interview with your host at calendly.com/Chad Smeltzer.